Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video we'll talk about the intuition behind different types of ensemble methods that are available in Scikit-learn. We look at the bagging estimator, forests of randomized trees, boosting, voting classifier, and stacked generalization. And this is one reference that I've listed here, which is on multi-class AdaBoost. So the ensemble methods that are available in scikit-learn are divided into these four main categories. The first is averaging, boosting, then voting classifier, and stack generalization. So the averaging has two different parts. So one is bagging, the other one is based on the forests of randomized trees. And within bagging, there are variations, testing, then bagging, random spaces and random patches. So these differ by the way the data set is sampled. And then we have on the tree side, we have random forest, extremely randomized trees, totally random trees embedding, which creates one hot encoded arrays. And then we have random patches. On then for boosting, we have AdaBoost, gradient tree boosting, and then histogram-based gradient boosting, which is experimental and it's much faster than the gradient tree boosting. And finally, there is the voting classifier and the stack generalization. So let's first look at bagging. A very simple intuition is if we have a set of data, what we do in bagging is we would sample uh, bits of the data, then process it to get a prediction, and then based on either if it's a classifier or regression, we would either take a vote if it's a classifier. So let's say if we have data about apples and orange classes, and we have 100 rows, what we can do is we can pick percentage of that. Let's say we pick 3 times, and we fit a model to that and predict the class if it's apple and orange. And if the two of these three predict that it as an apple, then we take a vote that two is a larger majority, and so we would classify that particular uh, record as sample as an apple. If it's a regression problem, then we can take the average of the predicted values and report that as the predicted value for a particular sample. Now, in scikit-learn, there are different ways this sampling can be done, and accordingly, there are different names associated with the types of methods. So if we have a data set such as shown here on the left, we have four features x1, x2, x3, x4, and we have one predicted value y. So the very first method of sampling the rows, that is samples without replacement. So if we pick the first row in this set, then we would not have that row available in this set to when we go ahead and sample the second time. So for without replacement, we can get these um, smaller data sets from the main data set, fit a model, come up with a prediction, and then we can get the predicted value based on if it's a classification, so vote for classification, and if it's a regression, then we can take the average value of all the predictions. Similar to pasting, which we saw here, we have bagging. So in bagging, what we do is we pull records from here to make a smaller subset of data, but then whatever records we pulled, we also keep them in the original data set. So when we sample next time, we have all the records from the original data set available uh, for the second sampling, and so on for the third sampling. And the steps thereafter are the same. We have these sample data sets, we fit a model, we come up with a prediction, and then based on whether it's a classifier or a regressor, we get the predicted value. Finally, there is random subspaces. So in the so far what we have done is we have sampled rows only. So we did not sample the features. In random subspaces, what we are trying to do is we take all the rows, but then we sample the features as shown here. So first subset has three features: x1, x2, x3. Then we have x3, x4, x2. Then we have x1, x3, x4. Uh, so we are sampling features, and again, the steps after these are we fit a model, get a prediction, and then based on if it's a classifier or regressor, we have the final predicted value. And there is also a version in which we can do both, sample the rows as well as sample the columns. That is, sample the records as well as the features. So here, as we can see, we have sampled these records and just three features out of four. Here we have these two records sample and three features and so on. And we can fit model to each of these, get the prediction, and based on again what the prediction is, if it's a classifier, you can take the majority vote. If it's a regressor, you can take the average value for the final prediction. So that was bagging. Now let's look at forests of randomized trees. So here the idea is somewhat similar. We have a data set. What we do is sample from that data set and then fit a tree, and then we fit a tree so that we are modeling it, and then we get a predicted value. So we can do the sampling multiple times, and so we can fit a whole we can fit many trees. And the word forest um, likely comes from this analogy where we are creating models of many trees, maybe hundreds or thousands of trees, and so many trees equals a forest, and so we have that forest word in there. So based on what the output is from each of these three models, we can come up with either classification or regression. If it's we can take a majority vote to classify, or we can take the average value to find the regressor predicted value. So in the randomized forest, what we are doing is we are taking random samples. So the idea with randomized forest, first of all, is our aim is to reduce the variance, or we want to reduce the overfitting. And to do that, what we try to do is introduce randomness in the modeling process as much as possible. And interestingly, these models that we are going to see, despite of adding the randomness, it it does two things. It reduces the overfitting, and it still gives better accuracy on unseen data. So it generalizes better when we introduce this randomness in the modeling process. So in random forest, what we do is we can sample again the records from the main data set, then fit a decision tree classifier in this case, and then based we can select which features we can use to as nodes. So based on the priority of nodes from top to bottom, uh, those are selected here. So based on the best value of Gini or entropy, and we then build the trees. So we build more than one trees, and the trees can be of different shapes. Here I'm showing the same shape. And then in scikit-learn, the docs suggest that for classification tasks, it is the probabilities that are averaged for to get the value for the predicted class, and therefore I'm showing here the probabilities, and we average those, and then That's how we get the predicted class. In extremely randomized trees, the only difference is while selecting when we are trying to select a feature for a particular node that needs to be split, the the value, the feature that is chosen is not the one with the lowest Gini value. Rather, it's a random value between the min and max Gini values for the features available at that time uh, when that node is being considered for splitting. And so that introduces another site of randomness in the modeling process that could help in generalizing the model and reduce overfitting. Here is a comparison of features, the parameters then that can be input to each of these classes: random forest classifier, extra trees classifier, and decision tree classifier. So here, both of these methods, random forest and extra trees classifier, do have the bootstrap option available, but in extra trees classifier that is set to false. So if you need to use bootstrapping, then you want to uh, set that to true. And bootstrapping is the same as what we have seen earlier in bagging, where we are repeatedly drawing samples from the main set of data and building a model, running predictions, and then so that the process of that is the bootstrapping. Now, I probably already know this. When we have a tree such as shown here, these methods also have attributes that can allow us to find feature importance. And the way the feature importance is found is based on the level, the position of that feature in the decision tree. So the higher up the feature is near the root node, then greater is the importance of that feature in uh, in describing the data to uh, achieve to get that particular predicted value. Now let's look at another variation of forests of randomized trees, which is totally random tree embeddings, and this is an unsupervised method, and it does not have a predict method. So this is used to transform an existing data set into a higher dimensional data set that has only ones and zeros instead of the original values that may be there in the data set. For example, here we have this data set with features, 4 features: x1, x2, x3, x4. So this can be randomly sampled, and then trees can be created using a base estimator such as extra trees regressor. And so after that, when we have a new data point or sample, we can pass that through each of these trees and get and the leaf to which that particular sample ends up in, that can be flagged as 1. All others can be flagged as zeros, and then all of these can be stacked together to get the final transformed matrix. And from what I've tried to find, the y value, when we try to fit the forest, these could be random uniform values that are used while the construction of this tree. Well, let's look at an example. Here we have this particular data set. Let's say we have 4 features, 1, 2, 3, 4, column wise, and then we have these 3 samples, which are the rows. Now, the tree that is created looks like this. If we pass this first data point, which is the first row, through this tree, the value for x0, so here we have 1, so 1 is less than 34, so it goes to the left. then we have to look at x3, is it less than or equal to 0.712. So x3 is 0, so again it goes to the left, and so the first row or the first data point or the first sample ends up in this leaf, the leftmost leaf. So we give this leaf a value of 1, then other two leaves have value of 0, and so here in the output matrix in the bottom right we have 1 0 0. Similarly, if we have the second row, we put that through this tree, the x0, in this case it's 9, is less than 34.581. So if we go to the left, then x3, which is 1, it is not less than 0.712, so it's false, and we go to the right, and so that sample ends up in this leaf. So we flag this as 1 and other two as zeros, so we get 0 1 and 0, and so that's what our second row is. And lastly we have 100, which is x0 right here, and 100 is not less than 34.581, so we go to the right, and in this case then we flag this as 1 and the rest 2 as 0, so we get 0 0 and 1, and that's what we have in the last row of the output matrix. And if we look at the parameters that we can pass to each of these methods, uh, we can set the number of estimators or number of trees that can be created. And remember, the more number of trees you have, more dimensions you'll be adding to the dataset. Also, max depth would also add more dimensions. And so that those are the inputs that can be fed into the random trees embedding. Now let's look at another technique which is called AdaBoost. That stands for adaptive boosting, where boosting means that we are continually updating the importance of each of the samples in the data. So each of the row has a specified weight, and we can change the or update the weight of each of those rows in each iteration based on whether that particular row or that particular sample was classified correctly or if it was classified incorrectly. And so here we have on the left hand side the data set with, let's say, three features x1 x2 x3 and a target variable y. In the very first run we start out with equal weight for all the samples, so all the rows, and here we set it to 1 by total number of rows, so 1 by 4, and that's 0.25. Next, what we do is we try to find which feature we can use first to calculate the first round of new weights, and for that we can use the criteria such as Gini impurity, and based on that the lowest Gini would be the feature that we can use as a root node, and we can then uh, calculate the error, and from that we can calculate the importance of that feature to predict the output value, and that can be used to calculate the new updated values of weights. Now what happens in these new values is that if a sample was incorrectly classified, then the weight of that particular sample or that row increases, and thus, as seen here, let's assume that the second row was incorrectly classified, and so we have higher weight for the second row. Now the next step is to resample the data set based on these new weights, and higher the weight, the chances that that row could appear more than once in the new resampled updated data set is more. So here we have second row appearing twice in the updated data set, and so on for, and the others remain just as one value. So this new data set with the can now be used again, can be cycled through here. So again we go through the loop of finding the Gini, finding the error, calculating the importance, and then calculating the weights, updating the data set. So in this iterative process, eventually you would stop when the maximums maximum of the sum importance by class for a particular class is more than the other class. If that happens after specified number of iterations are done, then we can assign that particular sample to the predicted class. Now here Scikit-learn implements a AdaBoost-SAMME, which is stage-wise additive modeling using a multi-class exponential loss function. So here in the algorithm would work like this. We initialize the initial weights as wi equal to 1 by n, which should be equal weights for all the rows. Then in the second step, there are 5 sub-steps. So we fit the classifier, so we fit the tree and then compute the error as shown here. And then from that error, we compute the importance as shown here. And using that importance, the weight can be updated. And after the weights are calculated, we need to normalize so that the total of the weights is equal to 1. So renormalizing the weight, and then again we can iterate through this loop for m number of times. So the number of trees specified, there were 100 trees, you'll iterate through this 100 times. And so by each each step you'll be gradually approaching, gradually the error would be reducing, and the predicted value should be approaching the observed values or the actual values in the data. And thus in classification problem, then the importance for uh, the importance given by each of those m trees to a specific class can be added. So if we have 100 trees and let's say 70 of those trees have a value of importance, total value, which is higher than the total value for the second class, uh, for the remaining 30 trees out of 100, then we assign the that data point to class which these 70% of the uh, trees have classified. And so here we have C of x is argmax sigma of alpha m, and that's the alpha we have from up here, which is the importance. Next we have gradient tree boosting, and in gradient tree boosting, and the concept is somewhat similar. We start out with the data set with, let's say, features a, b, c, target y. So in the first iteration, we assume that the predicted value is just the mean of each of mean of these target values. So here mean is 0.17. We assume that's the predicted value, and then we calculate the residual, that is the difference between the observed or actual value and the predicted value. So here it would be 0.12 minus 0.17, we get this value, and so on for the rest of these. Next step is to fit create a tree that predicts create a tree based on these features that predicts the residuals. And once we have that here, then based on this formula we can add these values. So we have the predicted value which was earlier this, and then we can add the residuals from here to that to get the new predicted values which are shown here. And when we do the addition, there is also a learning rate here shown by the parameter new that can also be added to avoid overfitting. And so again, we can then calculate the difference between the new predicted value and the actual value. So 0.12 minus 0.10, that gives 0.02, and so on for the rest of the samples or rows. And again, in the next iteration, we can fit a tree. In this case, we are fitting this tree shown here in the green, and the process is same. We fit this to predict residuals, and then we add all these previous values to this value, and then update, get a new set of predicted values, and we can iterate this through these steps until we have a metric uh, that is satisfied. And then based on the values for the metric, so in this case, because we are talking about regression, this could be MSE, so mean squared error. So and the smallest the difference between actual value and the predicted value would be where we could stop, and then that predicted value would be the prediction for that sample. And here gradient, the word gradient comes from the fact that in each iteration, what we uh, what we are trying to do is we are trying to minimize the loss, and to minimize the loss, we are setting the derivative of the loss function to 0. So let's say here in this mathematical form, and again this is from the scikit-learn docs, we have the yi hat, which is the predicted value, is equal to fm of x of I. This is a predicted value, is equal to sum of m from 1 to m. So m number of total number of trees we are creating, h of m hm x of I. And here the very first is we start with f of 0, and then in subsequent values that we calculate for the predicted y, we add the new value of hm of x to this particular previous calculated value. So that would be our learning rate into hm of x. And so what essentially we are trying to do is we are trying to find a predicted value that minimizes the sum of losses. So uh, hm is the argmin of lm, which is the loss, which is the sum of losses as shown here. And in this particular equation, this is a differentiable loss function that can be written as in this form shown here. So we have partial of Ly f of xi divided by partial of f of xi, and that's the gradient. And we can write that again in this form, where h of m is equivalent to the minimum of h of xi and gi within this summation I is equal to 1 to n. So what we are trying to do is find the value of h that minimizes this entire loss function right here. And there are different types of loss functions available with AdaBoost and gradient boost. So for regressor, these are the top values. So we have linear square exponential for AdaBoost, and least squares, least absolute deviation, Huber and quantile for gradient boosting. And for classifiers, we have exponential for AdaBoost, and negative binomial log likelihood, negative multinomial log likelihood, and exponential for the gradient boosting classifier. Another variation of gradient boosting, which is faster, is histogram-based gradient boosting. And this is, according to the docs, it's inspired by a light GBM method. And the way this works is the data set is, the samples are binned into integer valued bins, and so this binning helps in the process of creating trees where there is no need to sort the feature values, and that's why it makes it faster. And additionally, this particular method has support for NaN. We can also add weights to each of the samples. It can accept categorical features, and we can also add prior knowledge uh, to the as an input to the model. And additionally, this particular algorithm has low level implementation of parallelism using OpenMP. So overall, this is a faster algorithm, but it's an experimental method right now. And so we have to import the library experimental to run this. And here are the inputs that go into this method. We have learning rate that we can set, and then others are similar to what we have been seeing before. The loss can be set to auto in this case, and the maximum number of bins is 255. Next, these are voting classifiers. So as you may have already guessed, similar to what we have seen earlier in um, random forest or bagging, if there are more than two models that classify a data point into multiple classes, the class to which we assign that data point is the one that has the majority vote. So let's say 5 out of 10, or let's say 5 out of 6 predict class A, and just one predicts class B, then we assign that data point to class A. So that's what we have in voting classifier with type hard. So if we have three classifiers as shown here, predicted label is 1, 1, and 2. 1 has the majority because the class 1 has major, so we classify it as 1. On the other hand, there is something called a soft voting classifier. In this case, each classifier can be given a specific weight. So let's say classifier 1 has weight W1, classifier 2 has W2, classifier 3 has W3. So we multiply the weights with the probabilities, predicted probabilities for each of these classes, and then compute the total for each class. And whichever total is higher, we can assign that particular data point to that class. So here class 1 has higher uh, total, and so we assign the data point to class 1. And in case of regressor, if we have three regressors, then the average value would simply be the average of the three predicted outputs. Moving on, there is another interesting method which is stack generalization for classifier and regressor. In this case, let's say we have input x and y, target y. We can create either classifier or regressor models, predict the y values, then those y values are then stacked, and then there is a final model which is run on those stacked values to get the final predicted value of y. So that's a way method called stacked generalization, and we'll look at all of these examples when we do the actual implementation in Python. Finally, for code snippet, here we have another library, Ensemble. So from sklearn.ensemble, importing gradient boost classifier, and we have the dataset XY. So here I'm using this feature in Scikit-learn where we can easily create data for classification by using datasets.make underscore classification. You can specify the number of samples and number of features, and that's very easy to make X and Y, and we can then use the train test split to split that. I should have mentioned here from sklearn import model selection and then use, because trend test split would need that library. I've not included that here. Uh, then for CLF is equal to gradient boosting classifier and estimators is 10. So basically we are telling to create 10 trees, fit on X train, Y train, and then here this method is directly calculating the score. So um, routinely what we would do is we'll type clf.predict x test and then calculate the score based on that. Or alternatively, we could directly get the score by typing clf.score x test and then y test. So that was it for this video. I hope in this video you got intuition about ensemble methods that are available in scikit-learn. We looked at the intuition of bagging, randomized forests, boosting, voting, and stacking. I know we didn't go into the mathematical details of each of these methods, but uh, at least when using these methods, you'll have an intuition now as to what happens in the background and how the data is processed. If you have any questions, please let me know in the comment section below. I hope to see you all in the next video where we'll do actual implementation. Until then, please like, share, and subscribe. Thank you.